to Wadud Mia from the IT services part of Queen Mary, University of London. So although he'll be talking about resources that are available at Queen Mary, these are very much things that any university that does any sort of computational research will have access to. But sometimes within the music community, we may not necessarily think of the high-performance computing resources. So, Madhu, over to you.
Thank you very much. I'm from the Research Computing Services. I come from a physical sciences background, so I don't know that much about music research, but I think what I'd like to do is talk about high-performance computing and how possibly the music community could use this as a tool to expand their research. I mean, high-performance computing is traditionally being used by the traditional sciences, physics and biology and chemistry, but there's been an ever-growing adoption of high-performance computing across the different research communities, such as economics, business, even arts and humanities. So I think it's a tool that could be used, and I'll talk a bit about music research and the areas that people are pursuing. So let's talk a bit about background on high-performance computing and how it came to be. I mean, it's predominantly used as a scientific tool, and science has evolved over the centuries. I mean, it started off with empirical models where scientists looked through telescopes and microscopes to understand more about nature. And as their curiosity evolved, they developed idealized models to simplified equations that govern natural phenomena. And these were generally solved analytically because this is what people did. And then they were solved computationally because there were people exploring more complex phenomena, more difficult areas, such as fluid dynamics, structural mechanics, and they were solved computationally in high-performance computers. And they weren't able to solve them analytically. And then there's the so-called fourth paradigm called data-intensive computing. And examples of this are the Large Hadron Collider or Square Kilometre Array. And these experiments were creating lots and lots of data, and which were then visualized and analyzed. And going back to the talk earlier on, where lots of music files were analyzed. So this is an example of data-intensive computing. And high-performance computing is concerned with the computational and data-intensive paradigms. So we want to tell scientists what to do and how to do it. So this is visualized. So on the far left, you have a natural phenomenon. So scientists look at this, and you develop an idealized model. So L is an operator, U is some unknown function, your right-hand side is a known function, which is then discretized. Because computers are digital, they don't understand continuous models. So you have to discretize it. An example of this is a time-marching series. You then develop a computer program. It's a C4 loop here, which is then executed on your supercomputer. And that generates lots of data. So as a user, if you see lots of data, it's pretty much meaningless. So what you have to do is you have to visualize your data, try and get some insight into what created the data and try and understand the phenomena. From this insight, you publish a paper and get lots of money. So the applications that run on traditionally on a cluster are scientific applications, and they're very different from your traditional web applications or database applications. The application obviously has to be correct, but it also has to be numerically stable, and that's a key difference. So you have to choose the correct algorithm, and algorithmically it might look correct, but numerically it might not be correct. Then you have to have the correct discretization. As I said, computers, they don't understand continuous models. You have to discretize your problems. So you have to have the correct discretization, the spatial discretization as well as temporal discretization. And you have to use correct data type. And examples, typical examples of single and double position. You might have complex data types as well. The software has to be flexible, which means that you can parameterize it. So you might have a big application, and you might want to use different systems. So you have to be able to configure it. And another thing is that it has to be efficient, namely it has to scale well with a large number of processes. So that's parallel programming. So to measure your scalability, you have an equation here that should speed up. So T1 is the time that your application takes to run on a single processor, and TP is the time it takes for your program to run on P processors. So your speed up is given by this equation here, and this is dimensionless. So ideally, your speed up grows linearly with P, so that's known as good scalability. And occasionally, you also get your speed up greater than P, and this is known as superlinear speed up. And your efficiency is measured by this equation here, which is just speed up divided by number of processes. And ideally, you get 100% efficiency, but quite often you don't. And the efficiency depends on a number of things. Depends on the network topology. Usually we have factory, and you get more exotic topologies such as butterfly, 3D torus. It's how your different processes and how your computers connect together. And the amount of interprocess communication. So when you're working on a big problem, you've coded it, you've parallelized it, different processes will communicate quite often in physical sciences. And the number of processes you have. Quite often people run 64 process job, 128, but you can get jobs that run over 1 million processes. So they all have different characteristics. And the parallel algorithm you use, so how you decompose your problem to solve your global problem. And also the amount of code that you can parallelize. Quite often you might find a code that can only parallelize half of it, and the rest of it has to be done sequentially. And examples of this are your pre and post processing. That has to be done sometimes sequentially. So there are two types of high performance computing architectures. One is the shared memory. So the shared memory model is where each thread has access to memory as if it is local to it. So when you're writing your program, you access a variable. You don't have to do anything exotic to access that variable or that memory space. The other is the distributed memory model, where each process has its own memory space. And for the memory, it's the process to access another process's memory space. It has to do specific put and get calls. So it has to do something very specific to access another process's memory. The HPC clusters are generally distributed memory. Firstly, because they're cheap, and they also scale a lot better than shared memory supercomputers. And the cluster that we have at Queen Mary is a distributed memory cluster. So there's a great need for parallel computing. And one of them is because Moore's law has stagnated. The CPU frequencies have completely stagnated. They haven't increased for the last few years. They're around 3 gigahertz, 3.4 gigahertz. And they can only do a certain amount of work. So that's why you get multi-core desktops, servers, and even laptops. Scientific problems need more than one CPU, and hence the need for parallelization. And also, scientific problems are so large that it won't fit into the memory space of a single machine. Hence, you have to use a number of them. So there are only two reasons why you parallelize. One is the problem is taking too long on a single machine, and the other is that you need more memory than a single machine provides. So the way you parallelize is your problems are broken down into chunks, and each process works on its chunk. An example is you're analyzing a large number of music files, so each process can process one music file. And the most common parallel paradigm is a single program, multiple data. An example is vector addition. However, parallel applications do require some inter-process communication, or they could be completely independent. And again, another example is each process processing its music file. That can just be done without any inter-process communication. The parallel standard used research computing group is the message passing interface, and that uses this SPMD paradigm. A lot of applications use MPI. So this is the HPC Cluster Workflow. So at the top, you have your desktop machine, your laptop, your desktop PC. And you use that to log into your into the cluster. You can't actually go into the machine room and log in at the login node. So you have to log in via your desktop. And on your login node, you do things like development, you're building your application, you drop submission scripts, and very low intensity tasks, which you then submit to what's known as the scheduler. So there are three types of jobs. First is interactive. This is where, for example, if you're debugging your application. The second is a batch job, which is where you're submitting a sequential application. And the third is your parallel job, where you're requesting a number of processes that your cluster can allocate for you. And at the end of it, these do something, and they generally create data, which you can then analyze or visualize. That can be done on your login node. It can even be done on your compute node or your desktop PC, which you can copy the file over. We provide parallel visualization service. It's an application called ParaView. So if you have a very large data which you want to visualize, you can do that on the cluster, and that will be done in parallel. So this is a schematic diagram of your cluster and all the components. So as I said, you have your login node on the top right. So you authenticate and you log in, and that's your gateway to your cluster. And on the left, you have something known as the master node. This node carries out a lot of the administrative tasks of making sure the cluster is working correctly. But as a user, you don't have to know anything about that. So that connects to the what's known as the computational nodes, and this is where your work actually gets executed. Nothing actually gets executed in the login node, and that's connected via management network via gigabit Ethernet. And there's another network called the high performance network, and this is the InfiniBand network, which provides 40 gigabits of bandwidth. So if you have a large parallel application, it uses the high performance network to do the inter-process communication and execute your application. And we also provide a parallel storage system and a parallel file system, and that's a general parallel file system by IBM. And the way that works is we have a number of storage nodes, and they present the file system to the cluster onto the login node and on your compute node. And that connects to the backend SAN storage system. And that provides high bandwidth, parallel file access, and it provides high performance metadata. So if you have a large number of files, this storage system can allow you parallel access to these large number of files. So they're very different from like your NFS or AFS. If we run NFS on here, it'll completely cripple the storage system. And that's why we have a parallel file system. So you can store lots of your sound files onto the storage system and access them in parallel. So the login node, as I said, is your gateway to your cluster. So users usually edit programs and files. You do a lot of file management, copy files across to and from the cluster to your laptop, and you submit your jobs. You can monitor them and any other kind of low intensity task. And it uses SSH authentication. And remember, no computation is carried out on here. It's just a way to access the cluster. And the compute node is where the actual work gets executed. So the user home directory is exported to the compute node, which is the same as on your login node. And you can also request an interactive session. So you can say, I want an interactive session with 16 CPU cores because I want to debug my application. And as I said, parallel jobs use the high-performance InfiniBand network. And the high-performance network has very specific characteristics. It has 40 gigabits per second of bandwidth. And it also has 1.1 microsecond ping-pong latency. So it's a very low latency network, compared to Ethernet, which is gigabit bandwidth and around roughly 40 microseconds of latency, so it's quite high. And the CPUs have very high floating point capability, so you can do a lot of conversion between the different media formats very quickly. And your data can also be visualized and analyzed even on the compute nodes themselves. We have also storage nodes which give you parallel file access to your local space, to your home directory. And the storage system that we use is by IBM called General Parallel File System. And this connects to the backend storage area network. So they don't connect directly to the compute nodes. And it provides very high bandwidth, metadata performance for access to a large number of files. And the reason why we have number of storage nodes is that the file access is load balanced across the storage node, and gives you much better performance. And your home storage space limits are also managed. So there's a huge research area using HPC for digital music. There's research into using the HPC cluster as what's known as a hyper instrument for creation of new sounds. So you can actually use the cluster as a kind of virtual orchestra and use the nodes as virtual instruments. And you can coordinate this using the high bandwidth and the low latency network of InfiniBand. And you can treat this as a virtual studio technology. And there's work going on using the cluster for 24-bit and 192 kilohertz. There's ongoing work to work in the 384 kilohertz range using a high-performance cluster. So if you're interested in this, there's a link called hpcmusic.com, and there's very interesting research going on there. I'd like to play a quick sample of using the cluster compared to the desktop. I don't know if you can hear that. So this is running on the desktop PC. So you can hear that there's the sound clipping because of system overlay. The desktop is simply not powerful to create music. So I'll just quickly forward it to this is on the cluster. So you can hear there's no sound clipping because of the power of the HPC cluster. So I'll just skip that. Queen Mary has a HPC cluster that's available to the research community at Queen Mary. We can also open it up to MSc students and perhaps undergraduate students that are doing some kind of research work. The hardware that we have is enterprise class hardware and is optimized to run computation in data-intensive workloads. Applications are built from source and they're optimized and installed. And your home directory is backed up, so if you lose it, we can always restore it. Services are all secured using encrypted connections and protected using firewalls. We have a lot of user documentation and email for support if you need it. So that brings you to the end of my presentation. As I said, there's if you need any more information on using the cluster, there's an email here. There's a web address for more information on the cluster. And again, I'd like to encourage you to visit the hpcmusic.com webpage. So any questions?
Okay, questions?
Do you make any provision for using it outside of Queen Mary?
Yeah, we're part of the Mid Plus consortium. So this is a consortium of Warwick University, I think Nottingham. But if they're not part of the Mid Plus consortium, maybe we can open it up if you're collaborating with someone. But if you contact us on the email address, I can definitely get an answer for you. Okay.
Chris?
Relatedly, do you have any general idea for what facilities are available in other universities around the country?
Pretty much all research-intensive universities have a cluster very similar to Queen Mary's. So if you go back to your university, do contact your Generally, they're run by the IT services, and they should be able to put you in contact with the HPC admins. So yeah, most universities do have them. So,
Do you have the GPU power as well?
sorry?
Do you have GPU power level?
The computing department does. So if you're interested, we can possibly put you in contact with them so you can use it. But the group itself don't have GPUs at the moment. We just haven't had enough demand for them just yet.
I think, just to pick up on that, I think Stefan Bilbao in Edinburgh has been doing a lot of work with GPUs.
I know he has some.
Mm-hmm.
And our university is pretty using GPU in a general sense, not just in.
Dan, question.
I know that there's a bit of kind of a split between HPC and the kind of MapReduce.
Yes, there is.
So they're kind of like two different approaches to solving big problems.
Yes, that's right.
But so like Tillman was talking this morning about a Hadoop kind of way of doing
Mm-hmm.
things. Is there a way of doing that, using that approach on the system?
Yes, we can. I mean, there is a bit of divide between sort of compute intensive and data intensive, but I think they're kind of merging now because experiments are becoming bigger and bigger and creating lots of data. I think they are merging. But we can possibly, we can provide a kind of a big data service. We do provide a lot of data services to the research community. So we can tie in with the GPFS to deal with Hadoop workloads, and you just submit it as a job, and it will do the data analysis for you.
Okay, well, I think if there are any more questions, we'll save it for tea, but thanks very much again, Wayne.